Hello, everyone. Thanks for coming. My name is Saurabh, and my co-speaker is Kaushik, who is an applied scientist at Pinterest. And we are here to share a little bit about some of our recent work on scaling the inference of order of 10,000 length sequence recommendation models using CudaGraph and Triton kernels. So just a quick segue into what we are going to talk about. This is the model that we actually shipped on home feed. So what is that? Home feed is actually our primary product surface. It's the first page that people land on. It's a feed recommendation system. And just to give you a sense of scale, this model is used by about on the order of 10 million inferences of items per second for ranking. And we need to do this at extremely low latencies of less than 50 milliseconds P90 latency. The problem formulation looks something like this. You are trying to predict the probability of some kind of action, like maybe a click, given the features of a pin, some context about why you are trying to rank this item, and the activity of the user's history of what the sequence of activity looked like. And the key challenge that we are trying to solve as a part of this problem is how do we do a low latency real-time GPU inference of this system? And particularly, we want to focus on the user activity sequence. And in this specific model, we were trying to scale the user activity sequence by almost a magnitude of 20x compared to what we had before. And so now we leverage activity sequences of length 10,000 for our recommender models. Just a quick segue into the history of how this model evolved. The graph that you see here, every column represents the engagement volume increases. And as you can see, we started very early on in 2016 with tree-based models and so on. And then roughly around the middle, which is 2019, 2020, is when we moved to PyTorch. And so all of the remaining compounding wins that you see from the middle are basically all coming from the PyTorch ecosystem with CudaGraphs and GPU-based inference and so on. And in the recent past, we have actually scaled this quite a bit. We have started leveraging transformer-based models even for recommender systems. So we'll talk a little bit more about that in the next slides. So what does this model actually look like, right? It's like a typical recommender model architecture. Just to give you a quick glimpse of the characteristics of this model consumes about hundreds or thousands of features. This model does use very large ID embedding tables. And just to give you a sense of scale, the model, if you combine all of its parameters, is nearly on the order of billions of parameters. And the architecture is what you can see in the diagram. If you look to the bottom right of it, you can see that there is a section which says sequence features. And those sequence features are actually what gets consumed by the sequence transformers that sit above it. So these large sequence features, it's not a single feature. There are actually a collection of different sequences. And all of these are represented using the sparse sequence tensor formats because the user activities can be of varying lengths. And so the types of sequences that we actually work with are sequences of embeddings, sequences of different actions that the user took, or the sequences of timestamp. And there are two different architectures for this model. The first one, I've linked both the papers here. The first one is what we shipped in 2023. It only uses the real-time activity sequence of about order of 500 events. And the latest one that we shipped last year uses a batch plus real-time sequence of the order of length 10,000. So I think the interesting part about this specific problem is what happens when you try to scale this user activity sequence by almost 20x in size. And so before that, let me just give you a quick glimpse of what the user sequence processing in the inference server actually looks like. The inference server that I'm referring to is our own C++ built inference server. We use Torchscript, we use CudaGraph, and the GPUs that we typically rely on are A10G or L40S. So these are typically the 5 steps that happen in every single recommendation model that uses the sequence processing paradigm. So the first step that you commonly see is the densification step. If you look at the first diagram on the right, it's as simple as basically expanding the variable length user sequences into a fixed dense shape so that you can actually pack it into a mini batch and run inference on it. So this is very synonymous to how you do padding in LLMs. You basically want all the sequences to be of the same length, and then you can actually perform inference on it. So that's the first step is the densification part. The second step is the broadcast part, which is the second diagram below. This is very peculiar to ranking systems where you typically have a user's request and you're trying to rank many items for that same user. So there is this broadcast operation where the sequence or the prefix or the context is actually shared by many items that are getting ranked. The third step is something that happens across many different kinds of models, which is you typically have many different individual items or things you're trying to infer on, and you perform this batching operation. And these batches are typically present on your pageable CPU memory, and then you're trying to transfer it over into the pinned CPU memory and into the GPU memory for inference. The last two, which is the fourth and fifth, is what actually happens inside the model. So once the batches are already in the GPU, we do this sequence subselection. Like as I said before, like we need to run these models at very low latencies. So it's extremely hard to scale the transformer processing to nearly the order of 10,000 length. So what we end up doing is like we do this sort of a trick of doing a sequence subselection where every single candidate that you're trying to rank subselects very specific segments of the sequence that it can use for its own ranking. And then the last bit is, of course, the transformer execution, and Kaushik will dive into a lot of details about the fourth and fifth part. But before that, what I wanted to highlight is this is the part where like the model infra kind of needs to evolve together, because to ship something like this, you will encounter bottlenecks at nearly every single step of the way. So you will see bottlenecks across all the 5 parts. And so I'll try to just cover the first 3, which are more systems oriented. So what is the key challenge that we saw, right? The first is when you look at the first 2 steps, which is the densification and broadcasting steps, the issue is like very simple. Like you end up having very large mallocs and copies. And the reason for that is if you look at the length that I'm describing here, like 10,000 length, imagine you just have one sequence feature, which is an embedding of size just 32. And you're trying to run a mini batch inference of size 256. If you just multiply all of those, what you'll find is a single mini batch during inference, and just this one sequence feature can be 80 megabytes of payload. This is a very large memory allocation and copy problem. And the reason why this gets even trickier is because recommendation systems are trying to do this at very low latencies, and there are multiple CPU threads that are actually performing and running these things in parallel to kind of create the batches for inference. The second thing is also related to systems in the sense that when you are trying to perform inference, you're trying to batch multiple different items that you're trying to rank together. And once you have this batched tensor for all the features that you need for your ranking model, you need to do this like multi-step copy. And the most expensive part here that we found for our use cases was this multi-staged copy from like pageable memory to pinned memory and then into the GPU memory. And the way we run our inference servers is we typically run a parallelism of 8. So there are 8 parallel CUDA streams that are performing inference in parallel. And because of that, for this specific model, what we saw is if we started using these features for online inference, we nearly 100% saturate the PCIe bandwidth itself. So like no matter what kind of optimizations you try to do in the model, you basically just can't get the data fast enough to the GPU. So it nearly saturated all of the 16 gigabytes per second on 8NG GPUs. So what did we do? So we did 2 kinds of optimizations here. The first is request level sequence deduplication. Like conceptually, all of these sound simple. So I'll just try to quickly go over what they do. So if you look to the diagram on the right, this is a very typical scenario in ranking systems. So you have a user request. Say first user request is trying to rank 3 items, and the second user request is trying to rank 4 different items. What we can do is instead of actually broadcasting the sequence multiple times, you can just keep 1 copy of every unique user sequence that you see. So instead of actually maintaining 7 copies here, we just have 2 copies, 1 representing every unique request. The benefit here, this kind of looks something like prefixes in LLMs, where you want to minimize the preprocessing of those shared prefixes over and over. So what we do is like we just maintain the unique copy of each. And so the nice property here is now we can completely skip the broadcasting step, which is a very large malloc and copy operation. But this is not as simple as it looks. And the reason for that is your model still cannot distinguish which items belong to which sequences. And so what we had to do is actually rewire our entire training pipelines, data generation pipelines to the inference feature formats and the inference engine itself to now actually make the model accept 2 different inputs. So it accepts every unique sequence, and along with that, it also accepts a broadcast offset. What that broadcast offset tells the model is, okay, these 3 items belong to the first request, these 4 items belong to the next request. And the benefits of this property is like each sequence is now processed exactly once. So every unique sequence is batched exactly once, and it's copied from CPU to GPU also exactly once. So this substantially reduces the pressure on PCIe bandwidth, and it reduces minimizes the amount of bytes allocated and copied. And the last property that this enables us is now we can introduce custom model kernels. And the reason for that is we exactly know which ranked items belong to which request, so we can efficiently directly index into them without ever broadcasting the user sequences. The second optimization that we did is that of pinned memory arena. The idea is very commonly used in systems where you basically pre-allocate a giant chunk of contiguous block of memory, and then you just rewind and reuse it across different inference requests. And the idea is simple, if your batched tensor requires batching or any other operation requires a slice of memory, you just advance the pointer and return back the slice. And we actually allocate this arena beforehand. So as the server boots up, we pre-allocate this entire memory chunk, and we automatically estimate this based on the batch size that you are trying to run and the feature shape. And when you combine this with CudaGraph, what this effectively means is throughout your entire end-to-end batching, GPU inference, and returning back the outputs, you never allocate any CPU or GPU memory on the fly. Everything is pre-allocated. And this is a very nice property for low latency inference systems. The other thing that we did is instead of backing this memory by pageable CPU memory, we directly backed this with the pinned CPU memory, so there is no pageable to pinned memory copy anymore. And the pinned memory has a nice fast copy path into the GPU. This is the same as the Torch pinned memory that most people end up using. And so yeah, I think the benefits here are we skipped the on-the-fly allocations, and we skipped a giant copy from pageable memory to pinned memory. And why have I spent so much time talking about this? It's because usually when there is inefficiencies in the system during inference, we try to first target the model. But here we first try to optimize the system itself. And this is the result, right? If you look at the two different diagrams, the x-axis is the different batch sizes, which is 128, 256, 512, which is typically what we use during inference. And the y-axis is the time or the latency. And there is a lot more details in the paper, but what you can see is with these two optimizations stacked together, the total batch preparation and the copy time reduces nearly 85%. And the actual end-to-end batch P99 latency reduces 75%. This is a huge drop from where we started. And this was a critical part of actually optimizing just the systems part of it. So I'll take a pause there, and I'll hand it over to Kaushik, who can cover the modeling level optimizations that we did next.
Cool. Thanks, Saurabh. So I'm going to dive a bit deeper into the model side optimizations. And as you know, we use Triton kernels for this, and we rewrote our transformers using some custom Triton code. So before I go into the details, maybe I'll start by convincing you all why we need to use custom Triton kernels here. So the first reason is that recommender systems are very latency sensitive, and any increase in latency results in measurable engagement drops. And as we scale our sequence length from 500 to 16,000, we introduce several bottlenecks which blow up our latency and costs. And simple compiler-based fusion cannot leverage model patterns that you as a developer would know about your model. The second reason is because of user sequences and some properties of user sequences, which is that they follow power laws. So a few percentage of users have much longer sequences than the median sequence length. And so, yeah, and as Saurabh mentioned, user sequences are shared across multiple items that you're ranking, and we also store them in quantized formats. So we can actually come up with custom sparse tensor formats that are more efficient for storage and processing of these user sequences. And on the model side, to deal with this custom sparse tensors, we have Triton kernels, custom Triton kernels that work directly on this format without going through any densification step. And the final reason is that Triton supports AOT compilation, and this is really important for us because we use C++ inference and Torchscript, and this integrates very nicely. So this is how the flow would look like. We write Triton kernels in Python. Then we use the AOT compiler available in Triton to compile it to Cuban. And this is then linked as a custom operation in Torchscript. This is then used in our inference server, directly packaged into the model. Cool. Now that we have covered the reasons, maybe we can go into the transformers. So I'll walk you through a case study of two kinds of transformers we use in the home feed model, and how we leverage different particular optimizations for these problems to build kernels. So the first transformer is what I'll call a lean transformer because it uses a much longer sequence and it captures longer term history, but uses much smaller embedding dimensions, like 32. And these embeddings are usually content or engagement-based pre-trained embeddings. And the second transformer is going to be a wide transformer, also referred to as a TCAT. This has a much bigger embedding dimension and captures short-term interest of the users. And this one uses end-to-end learned IT embeddings. And we store both of these embeddings in quantized formats, either int8 or int4. So starting with the lean transformer, I'm going to draw a parallel to how flash attention works and compare like what particular advantages this has. So as I mentioned, the embedding dimension for this transformer is very low. So what that allows us to do is leverage the GPU SRAM much more effectively. So if you look at flash attention, the key advantage is of tiling. And you tile your QKV sequence tensors, and you load each tile into your GPU SRAM and compute your output block on the fly. And this allows you to not materialize the whole QK transpose tensor. For our case, for SKUT, since our weight matrices are really small, they can all fit directly into SRAM. So we have the 5 weight matrices, QKV weight projections, and the 2 weight matrices from the feed forward of the transformer. And we can load all of these directly onto SRAM. And instead of using 3 sequence tensors, we directly load the X input tensor, compute the projections on the fly, and then compute the output block directly. So this basically makes everything in place. And instead of loading these 3 large sequence tensors, you only have to load it once. And this resulted in significant latency improvements for us, around 6.6x improvement compared to flash attention 2. But of course, this is targeted at very small embedding dimensions of 32. So yeah, the second step is, even though we have this efficient transformer implementation, we really can't use the whole context length of 16,000 for real-time inference, just because it's too long for low latency inference. So we have some kind of sparse attention implementation that uses a top K selection. So this is pretty similar to how DeepSeek implements the sparse attention, but instead of it being learned, this uses pre-computed embeddings to do top K selection. So as Saurabh mentioned, we have these user sequences, and we have the candidates that link to particular sequences. And we have a fused kernel that directly goes from a quantized format for these sequences to a dequantized FP16, then computes the nearest neighbor with respect to the target or the candidate here, and does an implicit broadcast inside the kernel. And you materialize these 3 nearest neighbor sequences. So implementing a custom kernel for fusing all these operations together allowed us to improve our inference latency by around 30%. And we didn't have to materialize or densify our already sparse tensor formats in this. So now moving on to the second type of transformer, which is the wide one, also called DCAT. So this leverages our deduplicated user sequences that we do on the server side. So traditionally in recommender systems, the candidate embedding is usually fused with the user sequence, either by concatenation or adding directly to the embeddings. But the problem with this approach is that each sequence in your batch is now going to be different. And this does not allow us to leverage a key optimization here, which is we can break our transformer into 2 steps, self-attention and a cross-attention. So this is kind of inspired by KV caching, and I'll go into more details on how this works now. So if you take your user sequences, which is much less than the number of candidates you're ranking, you can compute the self-attention on them and get the KV cache from it. This KV cache can then be broadcasted across your entire candidate set. And since we know which candidate belongs to which sequence, we have the information necessary to do this broadcasting in a kernel. And once we have this broadcasted user sequence, we can compute the cross-attention with respect to the candidate embeddings and get the final ranking results. And this, we do this both in training and serving, and this allowed us to significantly improve our overall throughput of the system. So summarizing all the improvements we covered so far, we started off with this very unoptimized long context model that was blowing up our latency. We reduced it by 75% using memory arena and request deduping. Then we stacked our custom Triton kernels, which reduced it by 30% and then 30% further with our SKUT implementation. So overall, this resulted in around 250x P99 end-to-end inference latency reduction and significant infra cost reduction for us. So what are the takeaways from this? The first is that model server co-optimization is crucial. Our optimizations targeted both of them, and this was really helpful for stacking all these gains together. And second is like in terms of finding these bottlenecks, we used the PyTorch profiler to iteratively profile and find these bottlenecks in the model. And then third is that you can leverage optimization specific to your problem. The implementations out there, like attention, is targeted at a wide range of models, but your specific problem could have key observations that you could leverage for particular optimizations. And lastly, PyTorch is really nice, and that it can be easily extended with your custom implementations or custom kernels. And Triton is really dev-friendly. We massively reduced our development time when going from CUDA to Triton. And this is also easily integrates with our inference server and has AOT compilation support for that. That, I think, is the end of our presentation. These are the two papers that we covered the material from. And yeah, we can maybe take questions now or do it offline.
Yep.
Oh, I have a quick question. So yesterday, the Torch team mentioned that Torchscript was moving to deprecated status. How do you see the future of export?
Yeah, so I think Saurabh can take that.
Yeah, I think we also saw it during the presentation. Still thinking about how to approach it. I think what we saw, if I'm not wrong, yesterday is like I think the NVIDIA GPU support is still work in progress. It's not GA yet. So I think we'll probably work closely with the PyTorch team to figure out the next steps. I believe like in the presentation, they mentioned that they will potentially deprecate it in PyTorch 2.14. We are currently on PyTorch 2.6, so we have some runway. We probably need to figure out the next steps here. Does that help?
Yeah.
So thanks for the, I have a question regarding how you deal with like the super long sequence and you need nearest neighbor search to show like the signals there. So just curious, like you mentioned like you use the kernel. So basically, assuming that the entire user sequence is going to be the input into this single kernel to compute the sequence instead of you doing some sharding to distribute the compute on it and using some online algorithms to find the final update result.
Yeah, so this is done on the fly on the GPU. We don't use any distributed compute here. So we load the whole sequence on a single instance, and then the fuse kernel, without broadcasting the whole sequence, does the nearest neighbor search on the fly.
Does this also happen during training, or during training you just log the inference already?
Yeah, good question. So for training, we log the nearest neighbors only. Yeah.
Hi, noob question. Like, what are the hands of PCIe bottlenecks?
Sorry.
Like, how did you know that you are bottlenecked by the PCIe memory transfer, like host to device transfers?
Oh, how did we know we are bottlenecked by PCIe?
What are the hands of it also?
Sure. So I think the way we figured out is we use DCGM metrics, I think, which automatically exports the PCIe bandwidth usage. We monitor this for both training and serving. And we started seeing this effect where like the inference latencies were relatively low when we were trying to scale up, but like something between like we also have timers for like the CPU to GPU copies, and those started like elevating. So that's when we figured out like the PCIe bandwidth was getting saturated. If it helps, like one interesting part that we found out of this is like, given the PCIe configurations for these devices, like we expect about 32 gigabytes per second of throughput, but it actually saturates at 16 GB based on the cloud that you use. So, yeah.
I had a question about the densifications piece. Usually, like the sequences are fairly variable length. So, like, how did you use CudaGraphs for like variable length sequences and like.
All right, again.
Yeah, good question. So, yeah, so we cap our sequence length at 16,000, and for some of our sparse tensor formats, we store them with some padding. So, based on some P99 metrics, we estimate the maximum total sequence length that can exist in the batch, and we pad it at that length. Yeah, so we actually pad it to the maximum it's possible, so we don't have to do any splitting.